Hello everyone, welcome back. So today in this video we'll discuss about the line spectra of hydrogen atom. So in the previous video, if you remember, or if you have watched the previous video, we have calculated the energy of nth orbit. For different orbit we have calculated the energy, and also we have calculated the radius of different orbits. So the important thing from Bohr's model we have discussed that the energy was discrete. That means there was a different for different radius there was a different energy associated with it, and we have calculated in for the hydrogen atom. Considering the Bohr's model, we have calculated the energy of nth orbit is minus 13.6 by n square. So we have calculated this. If you remember in the previous video, that it is minus 13.6 by n square. We have calculated this number, we have calculated, and n is 1 2 3 4 like that. For n equal to 1 you will get 13.6 in ev, electron volt, right? So that means each orbit, if this is a hydrogen atom which is having only one proton and one electron, and this is the simplest atom for our discussion. Now this electron can have different orbits of different radius, and so is the energy. So each for this is for, let's say, n is equal to 1, for each cell will have a different energy associated with it, right? And also in the last video we have discussed that suppose the first cell will, if putting n equal to 1, it will have energy, let's say, minus 13.6 ev, and the second cell will have, if the electron is here, then it will have the energy minus 3.4 something. And if we'll find the difference of energy, then we have calculated, let's say in the last video, let's say this is E1, this is your E2. So E1 minus E2, the difference we have calculated at it was around 10.2 electron volt, right? So this is your E. So suppose the electron will jump from a higher cell to lower orbit, it will emit the energy. That's why we'll write, let's say it's E1 is the initial, or EI you can write, this is EF, right? So yeah, energy wise you can write E1 E2, but you will write this is, so let's say it is jumping from E2 to E1, so you will write E2 minus E1, E2 minus E1, so that it will be minus 3.4 minus of minus 13.6, so it will come up as 10.2 ev. That means when the electron will jump from the higher orbit to the lower orbit, it will emit this much of energy, right? And each energy will be associated with a wavelength. So Balmer calculated a empirical formula, he calculated. So Balmer calculated that your 1 upon lambda is equal to R 1 upon nf square minus ni square, and this constant is called Rydberg's constant. This is a Rydberg constant, and the value is 1.09 into 10 to the power 7 meter inverse, right? So this is the value of this R, that is the Rydberg constant. So the interesting thing is this is NF, means the final to initial, it is jumping, right? So from nth cell, suppose third cell to second cell, it is jumping. So nf to ni, right? So this is the final one, it is jumping to, suppose this is jumping to this one, so this will be your nf cell, this is your ni, right? So 2, this is let's say 1. So you can put the values of n. R is the constant, so you will get 1 upon lambda, or you can find out lambda, its reciprocal, and you will find that Balmer calculated this and he found that when the electron jumping from different cells, let's say from n2 to n1 or n3 to n1, then he got a spectral series of different wavelength. When the electron jumping from different cells to first cell, he got a different band of wavelengths, different wavelength associated with different energy. So he got a band of wavelengths that is called spectral lines. These are the spectra. Spectra means band of things, band of colors or band of wavelengths. So this is spectral lines. So he got that series is called let's say Lyman series, and when all the electron will jump to second cell, let's say from second third to second, fourth to second, or let's say fifth to second, then this is called Balmer series, right? So Balmer, according to his name, it's called Balmer series, Lyman series, Balmer series, then LBP we say like that. So Lyman, Balmer, Paschen, bracket and P bond. So the series are LBP, Lyman, Balmer, Paschen, bracket and your P bond. So you can, according to the different wavelength, you the series are named in that way, right? Yes. So this is your, if n equal to 1, if everyone is jumping to first orbit, then we can say it's a Lyman series, or n equal to 2 if all the radiation is to the first cell, then it is a Lyman one, and second one is Balmer series, then n equal to 3 Paschen, then bracket, TTE something like bracket BRACKET. So this is bracket series, right? And n equal to 5 P bond series. So if you want to remember it, so LBP like that you can remember. So this is what, when n equal to 1 means what? When all the radiation is to the first orbit, then this is your Lyman, this one. When the electron is jumping from the higher orbit to the first orbit, then your final NF is 1. Basically you can write NF is, this is NF, right? Initial can be anything, initial can be Ni, can be for NF1 your Ni can be 2, 3, 4 like that up to, right? So for NF2 Ni 3, 4, 5 like that, Ni can be greater than 2 basically. So it can jump from third to fourth orbit to second orbit, fifth orbit to second orbit, like that. That series of wavelength, that is called spectra, that is a spectrum, and that spectrum is called or named as Balmer series, Lyman series, and so on, right? So it will have, that series will have different wavelength. When it will jump from third to 1, it will emit with a different the light will come up with a different wavelength, and when it will go from lower orbit to higher orbit, it will absorb the energy that we have discussed in the last video also. Right, now experimentally, very from the Bohr's theory, this constant calculated, and it come up as uh, means approximately same result come up, so which is a good uh, your uh, proof for the your Bohr's theory also, Bohr's model also, and it made a way for the your quantum theory. The discreteness, the beginning of the discreteness started from this, and more proof come out with this Bohr's model. And also for this for his discovery, or for his model, Bohr's model, he got the Nobel Prize in 1922. And how from the Bohr's model it's matching, you can do that easily, that from third law of Bohr, you know that EI, the when the electron will jump from one orbit to another orbit, then you can write the energy difference is h nu. The energy difference is h nu, that you know from Bohr's model, right? So this is from Bohr's model. So this is Bohr's model, from Bohr's model, to know that the energy difference when the energy jump, so when the electron is jumping from third to second cell, E3 minus E2 is h nu. H is the Planck's constant, nu is the frequency associated with it, right? So you can write this one in terms of frequency also. We'll write that, wait, just so EI minus EF. Now E energy we have calculated in Bohr's model. If you remember, the energy we have calculated, En was of course this is the value, but before that also we have calculated this, how this 13.6 came up. En was minus me square, me to the power 4, 8 n square h square your epsilon naught square. So this was the energy we have calculated, and n is the number, means nth orbit, like first orbit or second orbit. So this is what the energy we have calculated for Bohr's model. If we'll use here, so your Ni and negative sign is there, that means Nf will come first. So we can take me to the power 4 as common, or you can write here, this is 8 ni square h square epsilon naught square. This is minus ef, also you can write this is nf, and this is negative sign is there, so another negative sign will be here. So me to the power 4, 8 nf square h square epsilon naught square. This is the energy difference according to Bohr's model, and this is your h nu. So you can write this is plus, this is minus, so you can write nf will come first and ni will be subtracted, and common you can take me to the power 4, 8 h square epsilon naught square is the common, and it will come up as 1 upon nf square minus 1 upon ni square is h nu, right? Which is your same as this equation, right? From the empirical formula of Balmer. So this is Balmer empirical formula, right? So this is same, right? How and from here also you can find out the value of r. So what you will do, you will convert this equation in terms of nu, because you know that one relationship between nu and lambda, that c equal to nu into lambda. This equation you know, this is wavelength and associated with it, and frequency equal to your speed of light. So you can write that from here, your lambda if you divide, so C by lambda equal to nu, or you can say 1 by lambda equal to nu by C. So 1 by lambda you can replace with nu by C, right? Or this one you can write as nu by C, or in terms of nu also you can write nu will become RC, R into C. If you want to write this equation in terms of nu, the frequency, so C you will multiply here, that RC into 1 by NF square minus 1 upon NI square. Fine. So this here we have nu, that means H I'll divide here. So whatever this constant, other terms, if you compare this two equation, so this part and this part same, and this part will be your okay, fine, yeah. So this part is equal to RC, because the nu equal to RC into this one, so this part must be RC. So if I'll rewrite this, so nu equal to H will be divided here, so m e to the power 4, that is 8 your h square h cube, basically h will be divided here, so h cube epsilon naught square, and this is 1 upon n f square minus 1 upon ni square. So this is your equation, and this value will be RC, right? So if you want to write this, your RC equal to, let's say this is from equation 1, so from 1 you can say RC equal to your m e to the power 4 8 h cube epsilon naught square, or you can say your R equal to, you will divide a C here. Fine. So from here you can say this is your Rydberg constant, and when you put all the values, mass of electron, charge of electron E 9.1 into 10 to the minus, sorry, 1.6 into 10 to the power minus 19 coulomb, mass 9.1 into 10 to the minus 31 kg, epsilon naught, H Planck's constant, C speed of light. If these are all the constant, if you just put in your calculator, and you will get that it should come up as approximately 1.03 into 10 to the power 7 meter inverse. So this is what your Rydberg constant from the energy that we calculated using Bohr's model, and from that model the energy difference between two orbit is your h nu, and if you will find out the energy difference and you will find out the constant, right, that constant is coming up this one, and this is your Rydberg constant, which is exactly approximately matching with your Rydberg constant that Balmer's experimentally he got this type of this result at 1.09 into 10 to the power 097 into 10 to the power 7, so it's 1.03, which is very close to the experimental result. So this result gives means this constant or it is verified that both are same, so it give the more confidence about the, we built a more confidence about the Bohr's model, that yes, the Bohr's model is a good one, this model is a accurate one, and this Bohr's model was widely used and widely means accepted by the scientific communities, that yes, this model is giving a result which is coinciding with the experimental results, right? So this is what all about the your hydrogen spectral, right, the spectral the line of spectra of hydrogen atom. Now you can calculate, suppose for example let us calculate one case. I'll not calculate in detail, you can do that. Suppose the question will be like that, suppose calculate for Balmer series, right? Calculate the wavelength associated with Balmer series when it is jumping, or when it is allowed to jump from your n equal to 3, right? So Balmer series means it's n equal to, final is it will jump to 2, that nf will become 2, right? So it's jumping from 3. So how will you calculate your frequency? Either if frequency will be asked, also you can calculate. If wavelength is asked, then also you can calculate. So you can use like 1 upon lambda equal to r into, the question is, it is jumping from basically initial ni equal to 3 to Balmer series, that means nf is your, this is Balmer, nf will become 2, fine. So you can use in your equation that r into 1 by nf square. So nf square, and f is your 2 square minus your ni square, that is 1 upon 9. So if you put, and the value will come up as, I have done Rydberg constant, you use square and differentiate. So if we calculate, it will come up, it should come up as you can use your calculator, or by hand also you can calculate. So it should come up as 1218 angstrom, right? It should come up as 1218 angstrom. You can do the calculation. I think I had done. So it will come up as 656 nanometer. Yeah. For Balmer series, we are doing the calculation. So it will come up as your 656.3 nanometer. So lambda will come up as 653.6 nanometer, I think. Yeah, 0.3, 656.3 nanometer. So your lambda will come up as this. So this is your question. You can try this. This is, one electron is allowed to jump from third orbit to second orbit, n3 to n2. So nf you will use 2, ni your initial is the starting, from where it is jumping, that is ni, nf is the final one. So when all nf is 2, it is Balmer. That's why Balmer series is written, that's why its nf will be 2. So you can use your formula, just you subtract, find 1 upon 2 square, 1 upon 3 square, this one subtract, multiply with your Rydberg constant, you should get 656.3. This is, yeah. So similarly, if it will jump from 4 to 2, then you will get a different lambda, right? So this all lambdas, they are within a spectra, and this series is called Balmer, right? So I think all you are clear about this spectral line of hydrogen atom. Of why we are always discussing about hydrogen atom, it's very simple, simplest form, only one proton and one electron, no other interaction is there, electron or proton interaction, this type of interactions are not there. So this is the simplest one. So our discussion is simplest. It's not very complex discussion, right? If other electrons or protons will come, more complex will be the discussion. So this formula is, or these spectral lines are good, means experiment wise they give good result for also hydrogen like atoms, like if you say hydrogen, helium or lithium 2 plus, right? So this type of atom also they give, means this your formula is applicable, or experimentally they are close, they give also close results. So if you have any doubts, you can write in the comment section. The clarification video I'll try to make another one. Right. Thank you for watching the video. See you in another video. Bye bye. Take care.